Breaking news. At precisely 02:19 a.m. UTC today, observatories across 3 continents registered a data convergence that should not have been possible. Moments ago, independent instruments, separated by oceans, politics, and even orbital altitude, produced the same visual reconstruction of an interstellar object already assumed to be understood. Today, the impossible just happened. What astronomers believed they were tracking as a fading interstellar visitor abruptly revealed a structure, clear, coherent, and disturbingly precise when its motion data was converted into a full visual model. At 02:19 UTC, this reconstruction stabilized, and when it did, everything we thought we knew about 3I Atlas changed. This is not just another update. This changes the way we interpret motion, mass, and intent beyond our solar system. If you want real-time cosmic updates as this story unfolds, hit like, subscribe, and stay with us, because what you're about to hear is still developing. Within minutes of the reconstruction lock, alerts propagated through NASA's Near-Earth Object Coordination Center, the European Space Agency's Space Situational Awareness Program, and internal networks at Harvard, Caltech, and the Max Planck Institute. The data was not raw imagery, it was something far more unsettling. It was a motion-derived shape model, a visual structure inferred not from light alone, but from how gravity, radiation, and space-time itself reacted to 3I Atlas as it passed through the inner solar system. And for the first time, astronomers were looking not at a streak, not at a point of light, but at a coherent form. This reconstruction did not come from a single telescope. It was assembled from a global lattice of observation. NASA's Deep Space Network stations in Goldstone, Madrid, and Canberra provided Doppler and ranging data. The Atacama Large Millimeter Array in Chile resolved subtle shifts in millimeter wave emissions. The James Webb Space Telescope contributed infrared spectral gradients, while Hubble added high-resolution astrometry from low Earth orbit. Ground-based optical observatories in Hawaii and South Africa filled in trajectory curvature at micro-arcsecond precision. Even the European Space Network's E-Strack antennas detected faint phase anomalies in background quasars as 3I Atlas passed between them and Earth. Before today, these datasets were analyzed independently. Today, they were fused. 48 hours before the reconstruction, nothing seemed unusual. 3I Atlas was already outbound, receding at approximately 32 kilometers per second relative to the Sun, its hyperbolic excess velocity consistent with an interstellar origin. Its temperature profile, averaging 68 Kelvin, showed no volatile outgassing. Its albedo remained low and stable. In short, it behaved like a cold, inert object. 11 hours later, subtle discrepancies began to appear. Trajectory residuals deviated by less than 0.04%, too small to trigger alerts, but enough to raise eyebrows among orbital dynamicists. 6 hours after that, a faint non-gravitational acceleration was detected, 0.00017 meters per second squared. Not thrust, not outgassing, something else. At T-2 hours, the anomalies converged. Spectral analysis from jwst revealed periodic absorption notches in the mid-infrared band, centered at 9.7 and 18 microns, normally associated with silicates, but arranged in repeating ratios. Meanwhile, the Atacama Array detected a low-frequency electromagnetic fluctuation at 1420 MHz, the hydrogen line, modulated in pulses lasting exactly 1.618 seconds each, the golden ratio. No known natural process produces that modulation. Then came the reconstruction. Using gravitational lensing microperturbations, scientists mapped how 3I Atlas bent background starlight, not enough to be seen directly, but enough to be measured statistically. Combined with Doppler shadowing and thermal inertia modeling, the object's motion was reverse-engineered into a 3-dimensional form. When the final render resolved, the room went silent. The shape was not spherical, it was not irregular. It was symmetric along 3 axes with repeating geometric features spaced at mathematically precise intervals. No natural accretion process creates that level of order. No known law of physics predicts it. Dr. Elena Moravec, a computational astrophysicist at Caltech, led the reconstruction team. Her simulations ran on a hybrid quantum classical cluster, iterating over 6 billion possible mass distributions. Only one solution fit all observed constraints. The model converged, she said quietly during an internal briefing, and once it did, it wouldn't diverge. That's not how noise behaves.
As the hours passed, teams worldwide began asking the same question. If this reconstruction is accurate, what exactly are we looking at? The mainstream explanation came first. According to Dr. Samuel Reed at NASA's Jet Propulsion Laboratory, the object could be a fractured interstellar aggregate, layers of ice and dust compressed under extreme pressure, then sculpted by anisotropic erosion as it passed through interstellar magnetic fields. In this model, the symmetry is an illusion, a byproduct of selective data weighting. Nature can surprise us, Reed argued. Given enough time and extreme conditions, improbable structures can emerge. But not everyone agreed. At Harvard, Dr. Annika Shah compared the reconstruction to known artificial structures generated in computational design. The match was unsettling. Repeating struts, load distribution curves, redundancy. If this were engineered, she said, this is what efficiency would look like. As debates intensified, a second wave of anomalies arrived. At 1942 UTC, one fragment, previously assumed to be debris, vanished from all sensors. Not faded, not occluded, gone. Simultaneously, magnetometers aboard 3 Earth-orbiting satellites registered a spike of 12 nanoteslas, localized and brief. Radio telescopes in Australia recorded a burst of broadband static lasting exactly 3.14 seconds, pi. Then silence. This was no longer random. It was responding. Internal communications grew tense. An encrypted memo circulated between NASA and ESA leadership recommending a temporary data embargo. The request was denied. The data was already too distributed. Too many eyes were watching. On Earth, subtle effects followed. GPS satellites reported timing offsets of several nanoseconds, harmless on their own, but synchronized. Migratory bird flocks in northern Europe altered their routes overnight. Power grid operators in Canada logged unexplained phase noise. No damage, just whispers. As the reconstruction footage leaked, blurred, incomplete, but unmistakable, the public reaction shifted from curiosity to awe. Governments issued calm statements. No threat detected, no cause for alarm. Behind closed doors, emergency committees convened. I remember staring at the rotating model on the screen, perfectly balanced, perfectly still. An object that had crossed light years of interstellar space, entered our solar system, shed most of its mass, altered its motion without propulsion, and now revealed a structure that looked intentional. What does that mean for us? Maybe we are not witnessing an invasion. Maybe we are not witnessing a probe. Maybe we are witnessing a relic, or a signal, or a technology so old that its creators are long gone. The universe does not owe us explanations, but sometimes it offers us questions. As 3I Atlas continues its silent departure, one final observation remains unresolved. The reconstructed model shows internal cavities, empty volumes arranged in a pattern that serves no structural necessity, unless they are not empty, unless they are waiting. What happens when it changes course again? What happens when the reconstruction updates? Subscribe to follow the next update, because this story isn't over.